Hi everyone. I hope you found this video helpful. If so, I'd really appreciate it if you could subscribe to my channel, like this video, share it with your friends, and leave a positive comment. Your support and encouragement motivate me to create more great videos. In this video, I've covered all the outlines in the syllabus, as shown in the figure.
Distance and displacement. Distance is the total length of the path traveled by an object. Distance is a scalar quantity, and its unit is the meter. Displacement is the directed distance from the start to the end points. Displacement is a vector quantity, and its unit is the meter. When a ball travels along a circular track from point A to point B, the distance traveled from A to B is half of the circumference of the circle. The displacement is the diameter of a circle, and its direction point from A to B, or downward or south. When a ball travels back to point A, the distance traveled from point A to return at point A is equal to the circumference of a circle. The displacement is equal to 0. This is because the ball has returned to its original position. Speed and velocity. Speed is the rate of change in distance. Speed is a scalar quantity and its unit is meters per second. Velocity is the rate of change in displacement. Velocity is a vector quantity and its unit is meters per second. The sign, positive or negative, in front of the velocity indicates the direction of the object's motion. The magnitude of velocity is equal to speed when an object travels in a straight line and does not change its direction. For example, a car travels with constant speed up and down the hill, as shown. While its speed remains constant, its velocity is not constant due to the changing direction of movement. A car is traveling at an initial velocity u for t seconds, reaches a final velocity v, and covers a displacement of s meters. Assuming constant acceleration, the average velocity is u plus v over 2. The total displacement moved is s meters. The total time is t seconds. The equation for displacement can be rearranged as s is u plus v divided by 2 multiplying of t. This formula is used for only constant accelerated motion in a straight line. Acceleration. Acceleration is the rate of change in velocity. Acceleration is a vector quantity, and its unit is meters per second squared. Therefore, the equation of acceleration is a equals v minus u over t. This formula comes from IGCSE. This equation can be rearranged as v equals u plus a t. This formula is used for only constant accelerated motion in a straight line. When v equals u, meaning that the acceleration is 0, there is no change in velocity, and the object moves with constant velocity. When v is greater than u, meaning that the acceleration is positive, the velocity is increasing, and the object is accelerating. When v is less than u, meaning that the acceleration is negative, the velocity is decreasing, and the object is decelerating. Motion graphs. Displacement-time graph. Its gradient is change in displacement over change in time, which is equal to velocity. So, the gradient of a displacement-time graph is velocity, while its area under graph does not have a meaning. Velocity-time graph. Its gradient is change in velocity over change in time, which is equal to acceleration. So, the gradient of velocity-time graph is acceleration. The area under graph in this case is a trapezium shape, which is u plus v over 2 multiplying of t. So, its area under graph is displacement moved. The graph shows how the displacement of an object moving in a straight line varies over time t, as shown. Recall that the gradient of a displacement time is velocity. As the gradient increases, the velocity increases. As the gradient is constant, the velocity is constant. As the gradient decreases, the velocity decreases. As the gradient is 0, the velocity is 0. As the gradient is negative and increasing, the velocity is increasing in the opposite direction. As the gradient is negative and constant, the velocity is constant in the opposite direction. As the gradient is negative and decreasing, the velocity is decreasing in the opposite direction. Sketch the velocity time graph of the object over the same time interval as the previous displacement time graph is shown. Recall that the gradient of a velocity time graph is acceleration. At this section, we draw the graph like this to represent increasing velocity at a constant rate. So, the gradient is positive and constant, indicating constant acceleration. At this section, we draw the graph like this to represent constant velocity. So, the gradient is 0, indicating no acceleration. At this section, we draw the graph like this to represent decreasing velocity at a constant rate. So, the gradient is negative and constant, indicating constant deceleration. At this section, we draw the graph like this to represent 0 velocity. So, the gradient is 0 and no acceleration. At this point, the velocity will change its sign, indicating that the motion's direction will change. At this section, we draw the graph like this to represent increasing velocity in the opposite direction at a constant rate. So, the gradient is negative and constant, indicating the acceleration is negative and constant. This shows that the velocity and acceleration are in the same direction. At this section, we draw the graph like this to represent constant velocity in the opposite direction. So, the gradient is 0, indicating no acceleration. At this section, we draw the graph like this to represent decreasing velocity in the opposite direction at a constant rate. So, the gradient is positive and constant, indicating the acceleration is positive and constant. This shows that the velocity and acceleration are in opposite directions. The area under graph above x-axis is the displacement moved to the right or upward. The area under graph below x-axis is the displacement moved to the left or downward. Sketch the acceleration time graph of the object over the same time interval as the previous velocity time graph is shown. At this section, we draw the graph like this to represent constant positive acceleration. At this section, we draw the graph like this to represent 0 acceleration. At this section, we draw the graph like this to represent constant negative acceleration. At this section, we draw the graph like this to represent 0 acceleration. At this section, we draw the graph like this to represent constant negative acceleration. At this section, we draw the graph like this to represent 0 acceleration. At this section, we draw the graph like this to represent constant positive acceleration. Exam-style question. Question 1. The variation with time, t, of the velocity, v, of the car is shown below. What is the average velocity of the toy car for the journey shown by the graph? Average velocity is calculated by dividing total displacement by total time. The total displacement is equal to the net area under the velocity time graph. The area under graph above x-axis is positive, which is equal to 3 times 10, resulting in 30 meters. The area under graph below x-axis is negative, which is equal to 6 times 5, resulting in negative 30 meters. Since the total displacement is 30 minus 30, resulting in 0. Therefore, the average velocity is 0 divided by 15, resulting in 0 meters per second. Question 2. A mass on the end of a spring bounces up and down as shown, after being released at time t equals 0. Sketch the graph of velocity varies with time. Recall that the gradient of the displacement time graph is velocity. At this point, the gradient is 0, causing the velocity is also 0. In this section, the positive gradient is increasing, causing the velocity to be positive and also increase. At this point, the positive gradient is maximum, causing the velocity to be maximum positive. In this section, the positive gradient is decreasing, causing the positive velocity is also decreasing. At this point, the gradient is 0, causing the velocity to be also 0. In this section, the gradient becomes increasingly negative, causing the velocity to become more negative. At this point, the gradient is maximum negative, causing the velocity is also negative maximum. In this section, the negative gradient is decreasing, causing the negative velocity to be less negative value. At this point, the gradient is 0, causing the velocity is also 0. Question 3. The graph shows how the velocity, v, of an object moving in a straight line varies over time t equals 0 to t equals t. Sketch the displacement, s, of the object in the time t equals 0 to t equals t. Recall that the gradient of displacement time graph is velocity. At this point, the velocity is 0, so the gradient of displacement time graph to be 0. In this section, the positive velocity is increasing, so the positive gradient of displacement time graph to increase. At this point, the positive velocity is maximum, so the positive gradient of displacement time graph is maximum. In this section, the positive velocity is decreasing, so the positive gradient of displacement time graph to decrease. At this point, the velocity is 0, so the gradient of displacement time graph to be 0. In this section, the velocity becomes increasingly negative, so the gradient of displacement time graph to be negative and increasing. At this point, the negative velocity is maximum, so the negative gradient of displacement time graph is maximum. In this section, the negative velocity is becoming less negative, so the negative gradient of displacement time graph to decrease. At this point, the velocity is 0, so the gradient of displacement time graph is also 0. Question 4. The graph shows how the acceleration of an object moving in a straight line varies with time. The object starts from rest. Sketch the graph of the variation with time of the velocity of the object over the same time interval. Recall that the gradient of velocity time graph is acceleration. At this point, the acceleration is 0, so the gradient of velocity time graph is 0. In this section, the positive acceleration is increasing, so the gradient of velocity time graph is positive to increase. At this point, the positive acceleration is maximum, so the positive gradient of velocity time graph is maximum. In this section, the positive acceleration is decreasing, so the positive gradient of velocity time graph decreases. At this point, the acceleration is 0, so the gradient of velocity time graph is 0. The equations of motion, or kinematic equations, are often called SUVAT equations. SUVAT stands for displacement, initial velocity, final velocity, acceleration, and time. These equations are used to describe motion with constant acceleration in a straight line. They involve 5 physical quantities: for vector quantities, displacement, s, initial velocity, u, final velocity, v, and acceleration, a, and 1 scalar quantity, time, t. We got the first equation from the definition of average velocity, like we talked about before. We got the second equation from the definition of acceleration, like we talked about before. We substituted the second equation into the first equation, like this. And then we rearranged the equation to get the third equation, like this. We got the fourth equation by combining the first and second equations. We rearranged the second equation to make time t the main variable, like this. Then we put this value for time t into the first equation, like this. We rearranged the equation to get the fourth equation, like this. When using kinematic equations, we place a negative sign in front of vector quantities that represent direction to the left or downward. Exam-style questions. Question 1. A bicycle brakes so that it undergoes uniform deceleration from a speed of 8 meters per second to 6 meters per second over a distance of 7 meters. If the deceleration of the bicycle remains constant, what further distance will it travel before coming to rest? First, let's calculate the bicycle's acceleration. Since all vector quantities in this case are directed to the right, we'll assign a positive sign to them. When the bicycle travels 7 meters, its displacement, s, is 7 meters, its initial velocity, u, is 8 meters per second, its final velocity, v, is 6 meters per second, and we need to find its acceleration, a. We can use the equation v squared equals u squared plus 2a(s). Let's rearrange this equation to make acceleration, a, the main variable, like this. We substitute v equals 6, s equals 7, and u equals 8. We get a equals negative 2 meters per second squared. The negative sign indicates deceleration, meaning the bicycle is slowing down to the left. Now, let's calculate how far the bicycle travels before coming to a stop from an initial velocity of 6 meters per second. We need to find the displacement, s. We know the initial velocity, u, is 6 meters per second, the final velocity, v, is 0, and the acceleration is negative 2 meters per second squared due to deceleration. We can use the equation v squared equals u squared plus 2, a, s, again. Let's rearrange this equation to make displacement, s, the main variable, like this. We substitute v equals 0, u equals 6, and a equals negative 2. We get s equals 9 meters. Question 2. A moving body undergoes uniform acceleration while traveling in a straight line between points x, y, and z. The distance xy and yz are both 40 meters. The time to travel from x to y is 12 seconds and from y to z is 6 seconds. What is the acceleration of the body? All vector quantities in this question are directed to the right. We'll assign a positive sign to them. Between points x and y, its displacement, s, is 40 meters, its initial velocity is u, its acceleration is a, and its time, t, is 12 seconds. We can use the equation s equals u, t, plus half of a, t squared. We substitute s equals 40 and t equals 12. And then we simplify the equation, like this. Between points x and z, its displacement, s, is 80 meters, its initial velocity is u, its acceleration is a, and its time, t, is 18 seconds. We can use the equation s equals u, t, plus half of a, t squared, again. We substitute s equals 80 and t equals 18. And then we simplify the equation, like this. We can solve these two equations together to find the acceleration, a, by eliminating of u, like this. We get a equals 0.37 meters per second squared to two significant figures. Free fall is the motion has only one force acting upon it, which is the gravitational force, weight, without air resistance, causing it travel with constant acceleration as 9.81 meters per second squared. We can use the equations for motion with constant acceleration in a straight line to describe free fall. Remember to put a negative sign in front of any quantities, like displacement, initial velocity, final velocity, and acceleration, that go downward. For example, a boy throws a stone vertically up into the air with a velocity of 6 meters per second. The stone reaches a maximum height and falls into the sea, which is 12 meters below the point of release, as shown in a figure. A. Calculate the velocity and time at which the stone hits the water surface. We set the upward direction is positive and downward direction is negative. When the boy throws a stone to reach the sea, its displacement, s, equals negative 12 meters, negative indicating that it's downward, its initial velocity, u, equals 6 meters per second, its final velocity equals v, its acceleration, a, equals negative 9.81 meters per second squared, negative indicating that it's downward, and its time equals t. We use the equation v squared equals u squared plus 2, a, s, to find the final velocity v. We substitute u equals 6, a, equals negative 9.81 and s equals negative 12. We get v equals negative 16 meters per second for two significant figures. The negative sign indicates that it's downward. Now, let's use the equation s equals u, t, plus half of a, t squared, to find the time, t. We substitute s equals negative 12, u equals 6 and a equals negative 9.81. We rearrange and simplify the equation, like this. And then we solve the equation for time t, like this. We reject the negative answer for time. So, time t equals 2.3 for two significant figures. B. Calculate the highest height at which the stone can be reached from the water surface. At the highest point, the stone's velocity is 0. When the stone is thrown up to its highest point, its displacement equals s, its initial velocity, u, equals 6 meters per second, its final velocity, v, equals 0 meters per second, and its acceleration, a, equals negative 9.81 meters per second squared, negative indicating that it's downward. We use the equation v squared equals u squared plus 2, a, s. Let's rearrange this equation to make displacement, s, the main variable, like this. We substitute v equals 0, u equals 6 and a equals negative 9.81. We get height, s, from the start point equals 1.835 meters. So, the highest height from C equals 14 meters for two significant figures. C. Sketch the graphs of the stone's motion until it hits the C, displacement time, velocity time and acceleration time. We will give going up is positive and going down is negative. At the start, the displacement, s, is 0. When the stone is thrown up, its displacement, s, increases until it reaches 1.8 meters upwards. So, we draw the displacement time graph, like this. The graph is a curve that decreasing gradient because its velocity is decreasing. From this point, the stone falls back to the sea, so its displacement decreases until it's back where it started. Then it goes down to negative 12 meters when it hits the sea. So, we draw the displacement time graph, like this. The graph is a curve that increasingly negative gradient because its velocity is becoming more negative. At the start, the velocity, v, is 6 meters per second upwards. When the stone is thrown up, its velocity, v, decreases from positive 6 to its 0 meters per second at the highest point. So, we draw the velocity time graph, like this. The graph is a straight line that constant negatively gradient because its velocity is decreasing at constant rate. From this point, the stone falls back to the sea, so its velocity changes direction and increases from 0 to 6 until it's back where it started. Then it goes down to negative 16 meters per second when it hits the sea. So, we draw the velocity time graph, like this. The graph is a straight line that constant negatively gradient because its velocity is becoming more negative at constant rate. The stone is falling freely, which means it's only affected by gravity. Gravity pulls it down at a steady rate of 9.81 meters per second squared. So, we draw the acceleration time graph, like this. This horizontal line shows that the acceleration is constant at 9.81 meters per second squared and downward. The experiment to determine the acceleration of free fall. We set up the experiment, as shown. The independent variable of this experiment is the height, h, that a ball bearing to fall. The dependent variable is the time taken, t, to fall. The control variables are the same mass, same diameter or same size of the ball berthing. The methods to measure the measurements as follows. To measure the height h from the bottom of a ball bearing to the surface of trapdoor using a rule. To turn on the electromagnet and a ball bearing falls towards the trapdoor. The timer starts to measure the time t as the electromagnet turns on and stopping as a ball bearing reaches the trapdoor. Repeat the reading of time t at same height h for 3 times, and find the average. Repeat steps 1 to 4 for 6 different heights as 0.10, 0.15, 0.20, 0.25, 0.30 and 0.35 meters. Record the results in the table. Plot the graph of time t squared on your axis and the height h on x-axis, as shown. The method of analysis of this experiment, as follows. When a ball bearing falls, the displacement, s, is negative h, indicating downward, the initial velocity, u, is 0, the final velocity, v, is unknown, the acceleration is negative g, the acceleration due to gravity, negative indicating downward, and the time is t. We can use the equation s equals u, t, plus half of a, t squared. We substitute s equals negative h, u equals 0, and a equals negative g. We rearrange and simplify the equation, like this. From the graph, its gradient is change in y divided by change in x, which is t squared divided by h. We rearrange the equation to get h over t squared, which is 1 divided by gradient. We substitute this equation into this equation. We get g is 2 divided by gradient. Exam-style questions. A student takes measurement to determine a value for the acceleration of free fall. Some of the apparatus used is illustrated in figure below. The student measure the vertical distance d between the base of the electromagnet and the bench. The time t for an iron ball to fall from the electromagnet to the bench is also measured. Corresponding values of t squared and d are shown in figure A. On the graph, draw the line of best fit for the points. So, we draw the graph, like this. B. State and explain why there is a non-zero intercept on the graph. The distance, d, is the distance the ball falls plus the diameter of the ball, because we didn't measure from the bottom of the ball. C. Determine the student's value for 1. The diameter of ball. We can read the y-intercept on the graph, which is 1.5 centimeters. 2. The acceleration of free fall. When a ball falls, the displacement, s, is negative d, indicating downward, the initial velocity, u, is 0, the final velocity is unknown, the acceleration is negative g, acceleration of free fall, negative indicating downward, and the time is t. We can use the equation s equals u, t, plus half of a, t squared. We substitute s equals negative d, u equals 0, and a equals negative g. We rearrange and simplify the equation to make g the main variable, like this. From the graph, its gradient is change in y divided by change in x, which is d divided by t squared. So, this is the gradient. We get g equals 2 times gradient. We find the change in y on the graph is 0.475 meters, and the change in x is 0.10 seconds squared. So, we get the gradient is 4.75 meters per second squared. And then we substitute gradient into this equation, so g equals 9.5 meters per second squared. The projectile motion. The projectile motion is a two-dimensional motion consisting of a horizontal component with uniform velocity and a vertical component with uniform acceleration due to gravity. This occurs when a constant downward force, such as gravity, acts on an object without air resistance. The vertical component of the motion has uniform acceleration, g, so we can use kinematic equations. The horizontal component of the motion has no acceleration, so the velocity stays the same, and we can only use one equation, shown here. The time t is the same for both components of the motion. Let's compare free fall and projectile motion. When a green ball thrown horizontally with speed u and a blue ball dropped from the same height at the same time, like as shown. At the start, both balls have zero initial vertical velocity. Every second, both balls fall the same displacement and have the same downward velocity. So, they take the same time to fall and have the same acceleration due to gravity. So, both balls will reach the ground at the same time and with the same acceleration due to gravity. But they will hit the ground at different speeds. This is because the blue ball's hitting speed is just v, y, downward, like this. And the green ball's hitting speed is the combination of v, y, and u using the Pythagorean theorem, like this. And its direction is at an angle theta to the horizontal, like this. So, the blue ball's motion is free fall, no horizontal component and a constant acceleration, g, in vertical component. The kinematic equations can use for this. The green ball's motion is the projectile motion, no acceleration and constant velocity in horizontal component and constant acceleration, g, in vertical component. When a ball thrown from the ground with a speed u at angle of elevation of theta, where air resistance is negligible. The ball travels along the curved projectile path, as shown. At the start, we can break the initial velocity, u, into a horizontal component, u, cos, theta, and a vertical component, u, sine, theta. As the ball goes up, the vertical velocity decreases, but the horizontal velocity stays the same. As the ball reaches the highest point, the vertical velocity is 0, but the horizontal velocity stays the same. As the ball falls back down, the vertical velocity increases downward, but the horizontal velocity stays the same. When the ball reaches the ground, the vertical velocity is the same as it was at the start, but opposite direction, and the horizontally velocity stays the same. At time t, the ball traveled a distance s, x, horizontally and a distance s, y, upward. We can break down its motion into horizontal component and vertical component, like shown in the table. The time, t, is a common factor for both the horizontal and vertical components of motion. The speed, v, at this time can be found by combining the horizontal velocity and the vertical velocity using the Pythagorean theorem, like this. The direction of the velocity, v, at this time is the angle beta to the horizontal, like this. Let's calculate the range, r, in terms of the gravity, g, the angle, theta, and the initial velocity, u. In the horizontal component, we get r equals u, cos theta, times t. Let's give this the first equation. The time, t, is the same for both components, so we need to find t in the vertical component and then put into the first equation. In the vertical component, the displacement, s, is 0, the initial velocity, u, is u, sine theta, upward, the acceleration, a, is negative g downward, and the time equals t. We use the equation s equals u, t, plus half of a, t squared. We substitute s equals 0, u equals u, sine theta, and a equals negative g. We rearrange and simplify the equation like this, and let's call this the second equation. We put the second equation into the first equation, like this. We use the fact that 2 cos theta sine theta equals sine 2 theta. So, we get the range r is u squared sine 2 theta divided by g. The equation for the range r is shown. The range r is longest when gravity, g, and the initial speed, u, are constant, which happens when sine 2 theta is 1. This means 2 theta is 90 degrees, so theta is 45 degrees. So, the longest distance, r, is achieved when the angle of projection is 45 degrees, with a constant initial speed, u, like shown in the diagram. The red path shows the motion of the object without air resistance. This is called projectile motion. The green path shows the motion of the object with air resistance. This causes the maximum height and the range, r, to be shorter. Exam-style questions. A ball is thrown from A to B as shown in figure. The ball is thrown with an initial velocity, v, at 60 degrees to the horizontal. The variation with time, t, of the vertical component of the velocity of the ball from t equals 0 to t equals 0.60 seconds is shown in the graph. Assume air resistance is negligible. 1. Complete the graph for the time initial the ball reaches B. The straight line graph is shown, which shows the vertical velocity of the ball. The gradient of the velocity time graph represents acceleration. This shows that the acceleration is a negative constant, which remains the same for the vertical component motion of the projectile motion. So, we draw the graph like this. 2. Calculate the maximum height reached by the ball. The area under the graph of velocity time is displacement moved. The vertical velocity is 0 at the maximum height. So, the distance moved equals area under graph between t equals 0 to t equals 0.6 seconds. This is because the vertical velocity is 0 at t equals 0.6 seconds. So, we get the distance equals half of 5.9 times 0.6 equals 1.77 meters. And the maximum height is 1.8 meters for two significant figures. 3. Calculate the horizontal component of the velocity of the ball at time t equals 0 second. We break down the initial velocity v. At t equals 0 seconds, the initial horizontal velocity is v cos 60 and the initial vertical velocity is v sine 60. In the graph, the initial vertical velocity is 5.9 meters per second. So, v sine 60 equals 5.9, and we solve for v like this. We substitute v in the initial horizontal velocity like this. So we get the initial horizontal velocity is 3.4 meters per second for two significant figures. On the graph, sketch the variation with t of the horizontal velocity. Label this sketch VH. The horizontal velocity remains constant throughout the motion. So we draw the graph like this.
I hope you found this video helpful. If you did, I would be grateful if you would subscribe, share, like and leave a positive comment. Your support will encourage me to create more content. Thank you.